All right, y'all, let's go over this test. So this is Ochem plus everything else. Right now, this is the SL version. For the HL version, it's one separate question I will do in a separate video or a separate answer key, but for now, we're just doing SL. So starting us off from the top, we're going to do our organic chemistry stuff. So number one, which formula represents an ether? Now, when we're looking at ethers, we're looking for R, of course, representing some hydrocarbon chain. It can be anywhere from one to infinity hydrocarbons, really. But we're looking for the single bond to oxygen, single bond to carbon. This OH at the end represents an alcohol. So I know that's not it. CHO. Now, CHO is going to represent our aldehyde. That's the C double bond O single bond H. All right, over here, COCH, perfect. That's a hydrocarbon chain next to an oxygen, next to a hydrocarbon chain, even though that one's one. But we have to be wary. Now, on this one, there's something special. We notice that carbon has no hydrogens bonded to it. So when I go ahead and I draw this C bonded to a C with three hydrogens, and then this one is bonded to an oxygen, but no other hydrogens. I have to then make an assumption that I'm actually double bonded to that oxygen. Then we have a CH3, and that would be a ketone, which does have the oxygen like you might expect, but it is not an ether, leaving us with D, CH3, bonded to an O, bonded to a CH3. So yeah, it's going to be D. Moving on, which are isomers of C5H12? First off, I see that this is 2N plus 2 hydrogens, meaning they must all be alkanes. So I'm not looking for any double bonds, single bonds only. Next, I see 5 carbons. So I'm just going to go ahead and count out the carbons. 1, 2, 3, 4, 5. Cool. Number 1 looks good. 1, 2, 3, 4, 5. Number 2 looks good. 1, 2, 3, 4, 5, 6. Ooh, number 3 is not good. 1 and 2 only. Which homologous series has the general formula CH2NO, where N is greater than 2? So we'll notice that we have an oxygen here, but we don't have the 2N plus 2. No, it's just 2N. That means that somewhere in this area, we actually have a double bond. So I'm going to be looking for things that have double bonds. Alcohols can, but not generally. Carboxylic acids also, we do have this double bond. We get COOH, but oh, that is one oxygen, two oxygens. We only want one oxygen. Can't be carboxylic acids. Ethers. Now, if we look back to number one, our ether right here in number one has two carbons and six hydrogens. That's 2N plus 1, or sorry, 2N plus 2. Turns out ethers still follow the alkane rule of 2N plus 2. So it's not going to be ethers. It's going to be our good friend ketone right here. That double bond actually reduces carbon's ability to take another hydrogen. As we're now learning, we create this kind of unsaturated uh, alkane, or actually in this case, we still may have that like kind of alkane chain, but we're unsaturated, meaning we can break that double bond to throw something else there. Moving on to number 4, which functional groups are present in serine? So right off the bat, I see H2N. That tells me that we have an amino group. So knowing that we have an amino group automatically says we can't have A and we can't have C because they don't have amino listed. Now, moving on to the next big group, I see a double two O's next to each other. That's a carboxylic acid, also known as a carboxyl group. All right, that eliminates B. Don't even have to look. Got to be D. But hydroxyl, let's find it. Oh, there you go, our hydroxyl group. All right, so it had to be D by process of elimination. All right, number 5, which compounds are members of the same homologous series? So homologous series means we're going to have this chain of increasing carbons, CH4, C2H6, C3H8. You can kind of think of it as like the alkane chain where everything's essentially the same. We're just increasing the number of carbons. So let's go through it. Propanol, propanone. Now the functional group is changing. Can't change the functional group. It's got to be the same functional group. Propane, propene, propine. Oh, we're going alkane, alkene, alkyne. Not it. Hexane 1-ol, hexane 2-ol, hexane 3-ol. This seems pretty close. We are moving our OH in this one 1 over every time. But the problem with that is these are just isomers. These are not part of a homologous series. They're structural isomers. So finally, we have D, ethanol, propan-1-ol, butan-1-ol. These are all going to be part of the homologous series of a hydrogen, or sorry, of a alcohol on the first carbon. All right, which is a homologous series? We just did this one, so let's go ahead and look. C2H4, C3H5, C4H6. That isn't really a pattern that we have. Doesn't really fit into anything. We can try and work it out. C2H4, that's going to be our ethene. C3H5, I don't know, I could maybe put a double bond here, double bond here, but even that would be 4. If I change one of these to a single bond, well, then we'd still have, oh, 2, 4, 6. No, it doesn't work out. We don't have any series here. Moving on to B, C2H2, C3H4, C4H6. This one seems like we maybe have something. We can even draw it out. C2H2. The only way to have that is with a single triple bond. C3H4. Let's check it out. 1, 2, 3. We'll keep that triple bond just because it worked once. Looking good. And now you might be realizing, oh, this is 2n minus 2. Well, bam, these is the alkyne series. And C4H6 follows that. 8 minus 2 is going to be 6. So for 6, it's B. We're looking at the alkyne homologous series. All right, what is the name of the substance using IUPAC rules? Well, let's identify a long carbon chain. Can do that first. I notice I've got this nice little 5-carbon chain. I could go this way. It's still 5 carbons. Don't really care. All right, then let's notice any functional groups. I've got an alcohol right here, and oh, is this an ethyl group? Yeah. All right. So if I'm now numbering these and I go 1, 2, 3, 4, 5, I know I will get the lowest numbers. So let's say pentane, but it's pentan 2-ol, and that'll represent that alcohol right there. And now I just have to represent the ethyl group. So that's on carbon 3, 3-ethyl pentan 2-ol. Sorry, that's pentan 4-ol. 3-ethyl pentan 2-ol, C. Moving on, which pair of compounds are structural isomers? Structural isomers. So once again, with structural isomers, we really just have to figure out how we can kind of move the things around. So propane and propene are not, because these are not even isomers. They have different number of hydrogens. Propene is going to have 2 less. Propanal and propanone. Ooh. Propanal and propanone are both carbonyls. And the fun thing about carbonyls is I know that they're going to have the exact same formula. Propanal is going to be CH3, CH2, CHO. Propanone is going to be CH3, CO, CH3. Oh, that to me looks like a structural isomer. We're just moving this double bond O from the carbon at the end in propanal and moving it right here to the carbon in the middle to make propanone. What is the general formula of alkynes? Well, it seems like we just figured that one out, 2n minus 2 back in number 6. So that's going to be C. Moving on to number 10. Which series is in order of increasing boiling point? So for a high boiling point, we want high IMFs, meaning that we want things like H bond. So we're looking for alcohols. So if I identify alcohols, there's an alcohol, there's an alcohol, here's an alcohol, here's an alcohol. All right, right off the bat, the only alcohol I see is in B at the end, at the highest. If we want to get really specific about it, we go from this first one having only LDFs, the second one introducing dipoles, with the ketone, and the third one introducing H bonding. We are literally going up the strength chart for IMFs. All right, what is the name of this compound using IUPAC rules? All right, same old, same old. Let's start by identifying the longest chain right here. And that is 6 carbons. So this is going to be hex. For this hex, we have to now identify, oh, what's that? It's a double bond. It's a hexene. So the question is, do we start counting the ene from this side over here? 1, 2, 3, 4, 5, 6. Or do we start counting 1, 2, 3, 4, 5, 6? Well, the truth is we want to make sure that the ene takes priority. So it's going to be hex 2-ene. So we're looking for hex 2-ene. And now we have a single group coming off the 4th carbon. So we're going to say 4-methyl. 4-methyl hex 2-ene, which is going to be Ra. Number 12, which is in the same homologous series as CH3OCH3. This, to me, looks just like the ester that we recognize. This is our ester. Whoops. Ester. And so we're going to look for another ester, which is ROR. So right here, once again, I see a ketone. That's a ketone. So that's not it. Right here, I see a carboxylic. Carboxyl. Nope. Right here, I see an alcohol. Alcohol. Or a hydroxyl. Oh, here's my magic ketone, D. Or here's my ether in D. All right, 13. Once again, let's find the longest chain. Oh, it tricks us. We go up here because we have 2 carbons. So that's going to be 1, 2, 3, 4, 5, 6. This is also going to be a hex. It's going to be a hexane because they're all single bonds. So now we just have to figure out the counting. Well, if we count from here, 1, 2, 3, 4, 5, 6. This would be a 3, 5, 3, 5 for our groups, or 1, 2, 3, 4, 5, 6. Otherwise, we have a 2, 4. And I'm going to go with 2, 4 because it's smaller. 2, 4 dimethyl. Di for the 2 methyl groups. Methyl because they're single carbons. Hexane. 2, 4 dimethyl hexane. Moving on to 14. A student has heated a known mass of zinc powder in an open crucible until there was no further mass change and recorded the final mass. What would the student be able to derive given this data? Well, I mean, we can produce the percent composition of zinc oxide. Once we find the mass at the end and the mass at the beginning, that's just straight up stoichiometry. Stoich. And if we have percents, then we can find the empirical formula because that comes from percent mass, where we just convert that back into grams out of 100 and then divide by the total number of moles. But molecular formula is a bit weird because if we had ZN2O, that would be the same percent as ZN4O2. Those would be the same mass percent. So we need something else. What we actually need is the molar mass or the relative molecular mass. So we can't find that one, but we can do 1 and 2A. Moving on to 15. All right. Luckily for us, they already give us the ideal gas law, PV equals nRT. But they're asking for the molar mass of the gas according to this data. Well, the thing is, in PV equals nRT, where is the molar mass? Well, it turns out it's actually hidden in the moles because you find moles by taking the mass of a substance and divide it by the molar mass. So we're just going to go ahead and substitute that in for moles. So PV equals mass divided by molar mass times RT. All right, now all we have to do is just isolate molar mass. This is algebra. So molar mass, I'm going to do the whole swaparoo. Just going to swap what's on the bottom here with what's on the top here, as you can do in math. And what I end up getting is the molar mass is equal to the mass times R times T divided by PV. So this is going to be, this is going to be our mass, which is 40.0 times R, 8.31 times T. Now there's another quick issue. T is in degrees Celsius, but R is in Kelvin. So we're actually going to have to do the conversion. We have to convert from Celsius to Kelvin. So in doing that conversion, we will find that T is equal to 290 Kelvin. We're just going to go ahead and take our answer from there to 90 and divide it by our pressure, 98, and our volume, 220 centimeters. Oh, here's another problem. 220 centimeters cubed. That doesn't fly. We use decimeters cubed. So we're going to have to go ahead and convert that by dividing by 1,000. So we're going to say times 0.220. So when we solve this out, we're going to find out that we've just rewritten A all over again. All right, which statement best explains first ionization energy of sulfur being lower than that of phosphorus? Now for this one, I am going to bring out my periodic table. I can't really do much without it. I'll be honest, a chemist is lost without their table. So sulfur has more protons than phosphorus. Does it? Yeah, it does have more protons. It does have, in fact, one more proton. Now the question is, does that explain the ionization energy of sulfur being lower? Because to me, that would see that our Z effective might actually be higher. The effect would be greater. So sulfur having more protons would counteract this. So it can't be that one. So let's look at the next one. Phosphorus does not have paired electrons in the outer p sublevel. Well, if we once again look at our periodic table and we look at our p sublevel, they both have p3. So sulfur has p3p4 and phosphorus has 3p3. So if we look at the electron diagram and we look at our 3p sublevel, and I'm going to do the same thing for phosphorus, 3p sublevel. Sulfur has, would you look at that? Sulfur has, ooh, actually I messed that one up. Sulfur only has 4 electrons. All right, so with sulfur's 4 electrons in the p sublevel, we see that one's actually paired before the others. Well, phosphorus has unpaired electrons. And the thing we know is that electrons repel each other. So if sulfur's electrons in the p sublevel have one pair, it's kind of uneven, and we're going to feel that kind of repulsive force. And that's going to actually shift that electron out a little bit easier. And so it turns out our answer is in fact B. Phosphorus does not have that paired electron. So we're going to have sulfur having a lower ionization energy than phosphorus. All right, 17. In the following unbalanced equation, X represents an element. Which oxide reacts with water as shown? The only info we really have is XOH2. We know that hydroxide has minus charge. And we actually have 2 of them. So whatever X is, X must have a 2 plus charge to balance that 2 minus. So it can't be sodium. Sodium has 1 plus. Oh, it's magnesium. And we knew it was going to be a metal too, because it was going to be a metal oxide, so it would have that positive charge. All right. What is the enthalpy change for the following reaction? So we see that methane plus water reacts to form carbon monoxide and hydrogen. So going through this list of reactions, I'm going to try and order them so they have the right things on the right side. First off, with this first one, identify CO. It's on the correct side, so I don't have to make many changes to this. But the one thing I noticed is that we have 2 carbon monoxides, but we only have 1 carbon monoxide here. So I'm going to just throw it out that we're going to have to divide this whole thing by 2. Divide this whole thing by 2. Because whatever I do to the reaction, I'm going to also do to the enthalpy change. If I have half the reaction, I have half the enthalpy change. All right. Moving forward, I notice that here I have my carbon on this side, but carbon's already on this side and it's not here, which means this carbon's going to have to move over. We are further supported in this decision by noticing that hydrogen also needs to be on the product side. And we're even further supported by noticing that methane needs to be on the reactant side. So we're actually going to go ahead and multiply this whole thing by -1 because we're going to take the inverse of this reaction. We're going to actually take this reaction and go backwards with it. So instead of losing 74 kilojoules per mole, we're going to reverse the reaction and add in 74 kilojoules per mole. All right, lastly, we have 2H2 plus O2 reacts to form 2H2O. Once again, I notice H2O should be on the reactant side, and hydrogen should be on the product side. Also, I have 2H2O here, but only one H2O there. So I have to kind of combine what I did before. So now I'm going to multiply by a -1, but also divide by 2. So when I add all these enthalpy changes up, like I add these reactions together, I get -222 divided by 2 plus 74 plus 484 divided by 2. So that's 111 plus 74, sorry, -111 plus 74 plus 242. Well, that only correlates to one answer, which is B. So this took me a while doing it this way, but what you just really want to do is quickly instead recognize what needs to happen to the reaction and then identify those parts in the equations. We could have easily taken C and A out because they're -74s, and we could have easily taken D out because it did not have the right coefficients and was not divided by 2. The process of elimination would have gotten us there a bit faster. All right, number 19. Which calculation determines the initial rate of reaction? Well, the initial rate of reaction is the rate tangent to the start. So what I'm going to do is I'm going to try and draw a slope equation or a slope that matches the slope at the start. I think that's pretty good if I don't say so myself. And I'm going to try and identify what kind of math I can figure out from this. Well, 40 is quite nice. I'm starting there because that's my initial point. And as I look down at my line, let me actually go ahead and extend it further. Trying to keep it tangent still. Perfect. At that tangent, I notice a couple things. I don't really run into any nice points, but I do run in about half right there. And if I go ahead and identify half of 20, that's going to be 10. So my slope is going to be a decrease from 0.4 to 0.2, and over the time, 10 minus 0 seconds. So that'll be it. The other reactions, A indicates from 0.4 to 0.19, 20 to 0. So A indicates the line from here to here. And my issue with that is that's not initial. That's between our first data points, or not even our first data points if we have them. B indicates from here. I'm going to change colors. B indicates from our starting point all the way to here. Once again, that's not initial. And lastly, C indicates the entire reaction. Once again, that's not initial. That would be average. So D is the only one measuring initial. What are the products formed by the neutralization of nitric acid, HNO3, by calcium hydroxide, CaOH? Well, I'm just going to take the anion and the cation, put them together, and I get calcium nitrate plus, and I have hydrogen and OH, HOH, which I can just reorder to be H2O. Calcium nitrate and water, B. All right, moving on to 21, we have to go back to galvanic cells. So what statement is correct about the ions in a cell assembled from these half cells? Well, first off, we're going to figure out which one's going to be oxidized and which one's going to be reduced. I notice a greater negative potential here, which means it would have a greater positive potential if we reverse it. So zinc really wants to actually become zinc 2 plus 2 electrons. So I'm going to go ahead and make that one positive. So this kind of gives me an idea of what's happening. Zinc is going to be oxidized. It's going to be losing electrons, while nickel is going to be reduced. It's going to be gaining electrons. So if zinc is oxidizing, that means it's throwing these 2 plus ions into the solution. That means that half cell, the zinc half cell, is going to become increasingly positive, increasingly positive, increasingly positive as more zinc ions go in. So right off the bat, A has to be correct. Negative ions must flow into the zinc half cell from the salt bridge. We have to balance it. What is the correct comparison of H and H bond angles and NH2 minus NH3 and NH4 plus? Well, we looked at this a little bit in class, but if we have NH2 minus and we draw it out, we kind of get this nice shape that almost looks like water. NH3 and NH4 plus. And as we look at these shapes, what we notice is that the most the most negative parts, the most repellent parts to each other are going to be these pairs of electrons because they're just pairs of electrons close to the element. And they're going to start pushing on these bonds. And now on NH2 minus, they're pushing really strongly. It's 2 pairs pushing on 2 bonds. NH3 has 1 pair pushing on 3 bonds. And NH4 doesn't have any pairs pushing on any bonds. So because the bonds in NH4 aren't stressed in any way, these are just going to be tetrahedral and 109.5. But in NH3, we're going to have that stress, which is going to bring these closer together. And we're actually going to have some sort of compression, probably closer to like 107 degrees. And then even more so uh, with uh, with NH2 minus. We have so many more. So the bond angle is going to be much smaller NH2 minus, then NH3, then NH4 plus. All right, what information does a molecular formula provide? Well, let's just take a molecular formula like H2O. Simplest ratio of atoms in a molecule? Sometimes, but also like C8, H18 doesn't. That does it doesn't give us the simplest ratio. No. Actual number of atoms? Yeah, that's true. All right, don't even have to go further. Number of molecules in a mole, though, that's just Avogadro's number. Avogadro's number. So who cares? And then D, types of bonds in a molecule, that's going to be our Lewis diagram. All right. Now to the long answer. Chloroquine is a medication used to prevent and treat malaria. Draw a circle around the secondary amino group. Secondary, meaning that we are attached to 2 carbons. All right, right there, secondary amino group. State giving a reason whether carbon or nitrogen is the most electronegative element. It's going to be nitrogen. We know it's further to the right and up on the periodic table, but realistically, it is smaller. It has a smaller atomic radius, meaning the electrons can be closer. And if those electrons are closer, they'll feel a greater force of attraction due to the electrostatic interactions. The other reason you might want to say is that it's got a larger effective nuclear charge. And that's just going to be the force that the nucleus puts on the electrons. All right. This reaction can be done with a copper catalyst. State the ground state electron configuration for copper. Well, if we look at our periodic table, which I'm just going to pull up again. Whoops. Come on. Copper. Oh, there. Oh, gosh. I have to grab my pen. Copper's right here. With copper right here, we can go ahead and count. It would be, we would think 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. But copper is one of those elements where, and we're going to do argon. just so that we get the one before we go in. Copper is one of those elements where it's going to say, I'd rather have a complete D shell than a complete S shell. So it's going to say 4s1, 3d10. You could also have said 3d10, 4s1, both are correct, but still the argon through. All right. Annotate the Maxwell-Boltzmann distribution curve showing the activation energies for the catalyzed and uncatalyzed reactions. Well, you just kind of put it somewhere. We'll say EA uncatalyzed. Sorry for my Z's, but I'm American. You could then see that when we have a catalyzed reaction, a catalyst lowers the activation energy. So we'll do a new one somewhere lower. And this will be our catalyzed. EA. And there's your points. You can indicate that you have more under the curve with our catalyzed, therefore more reaction. All right, explain referring to Maxwell-Boltzmann distribution curve, the effect of catalyst on chemical reaction. It lowers the activation energy, therefore more particles can, can react as they have the requisite energy. You can also say it provides an alternate route. Provides an alt route for reaction. And I'm abbreviating. Please don't abbreviate on your actual IB. All right. 25, gasoline, petrol, biodiesel, and ethanol are fuels, and we have a bunch of data on them. Calculate the energy released in kilojoules from the complete combustion of 5 decimeters cubed of ethanol. Y'all, I'm going to do my favorite thing, which is use stoichiometry for things that aren't even really stoichiometry. But I'm going to start with 5.00 decimeters cubed of ethanol. Now, I'm trying to cancel my unit, so I'm going to drop it like it's hot. Decimeters cubed ethanol. And I only really have that data one place. I see that I get energy density is measured in kilojoules per decimeter cubed. And if I do that of ethanol, I get 21200 over 1 decimeter cubed. Oh, look, I just use the same dimensional analysis I always do. And I get 1.06 times 10 to the 5th kilojoules. All right, state a class of organic compounds found in gasoline. Gasoline, petrol, also sometimes we think of things like octane or whatever. Those are alkanes. Ane, whatever. Mainly hydrocarbons, chain link, C4 to 12. Those are going to be alkanes. If you know the smell and you have an idea, you can also say cycloalkanes, or you could just say arenes. Any and all will give you the point. A mixture of gasoline and ethanol is often used as fuel. Suggest an advantage of such a mixture over the use of pure gasoline. Well, you use less gas. Oops, gas. In other words, you're using less fossil fuels. So right off the bat, just the fact that you're using less fossil fuels is enough to say, or at least maybe not just less, but using less gas or using fossil fuels maybe more slowly. And because we're using fossil fuels more slowly, that's always much better. You're going to have lower carbon emissions. If you literally look at these, ethanol has far less carbon than gasoline. So you're going to have lower carbon emissions because you're burning less carbon. Other things you can talk about is that we're going to have a more complete combustion. So you can get points in many, many different ways. All right. When combusted, all three fuels release carbon dioxide as well as particulates. Contrast So contrast, they only want differences, no similarities. A lot of people give similarities. When they say contrast, only differences of how carbon dioxide and particulates interact with sunlight. Real easy. One, we got to include sunlight in our discussion because it's right there. But two, we just got to say what we see. Particulate interacts with sunlight. Now, you should be specific in how it interacts, such as either reflects, scatters, absorbs sunlight. So, like, you can say any of those things. CO2 doesn't. Light goes through CO2. You could also say only absorbs IR, which is true. It contributes to greenhouse gas. It contributes to the greenhouse effect by absorbing IR. But that distinction is enough. Either way, that's how you get the point. Methane is another greenhouse gas. Contrast the reasons why methane and carbon dioxide are considered significant. Again, contrast to the differences. Well, first off, there's more CO2 in the atmosphere. One difference, done. Uh, based off the same thing, CO2 contributes more to global warming. The other main difference is that methane, CH4, has a larger greenhouse effect, basically meaning it absorbs IR better. You need both of those to get both points. All right, last question. Ammonium nitrate, NH4NO3, is used as a high nitrogen fertilizer. State with the reason whether the ammonium ion is bronzed with lowering acid or base. So let's look at NH4 plus. It decomposes into NH3 and H plus. Oh, the definition, it is an acid because it donates H plus. That's it, straight up. Calculate the pH of an ammonium nitrate solution with an hydronium ion concentration of 1.07 times 10 to the negative fifth moles decimeters to the negative third. Use section 1. They mean find the pH equation, which basically says a negative log of our value, 1.07 times 10 to the negative fifth. And when we plug that into a calculator, we get our nice value of 4.97. pH is unitless. Don't try and throw any units over there. They don't want them. All right, write the chemical equation for the decomp of right here, solid ammonium nitrate, solid NH4NO3 with our state symbol, solid, decomposes into gaseous dinitrogen, N2 monoxide, O, plus liquid water, oh, sorry, gaseous plus liquid water, H2O, liquid. All right, so what we have to do is make sure our equation is balanced. I see 2 nitrogens and 2 nitrogens. I see 4 oxygen or 4 hydrogens and 2 hydrogens. So I'm going to go ahead and just give it a quick little 2 in front of H2O. Cool. Hydrogen balance. And then I see 3 oxygens and 1, 2, 3. Perfect. Balanced chemical equation. We're done. You didn't balance it, you did not get the points. Calculate the volume of dinitrogen monoxide produced at STP when 5 grams of sample of ammonium nitrate decomposes. Use section 2 of the data booklet. When you use section 2, you find out that 1 mole of a gas is equal to 22.7 decimeters cubed volume. So 1 mole is approximately 22.7 liters. We're going to need that conversion because this is all this is, conversion. So 5.00 grams NH4NO3. I'm going to convert grams to mole. 1 mole NH4NO3. And I'm going to do that using the molar mass, which I know the molar mass by using the periodic table is about 80.09. That's adding up 2 nitrogens, 3 oxygens, and 4 hydrogens. and sorry, I believe that's 0.06, not 0.09, grams of NH4NO3. You'll notice I'm keeping my units throughout because I don't want to make a mistake. I know from looking at my balanced chemical equation from the one above that for every 1 mole of ammonium nitrate, NO3, I have 1 mole of dinitrogen monoxide. Now I'm looking for volume. So I bring that over here and I see that 1 mole of dinitrogen monoxide should be equal to about 22.7 decimeters cubed of dinitrogen monoxide. I'll cancel my units. Grams, grams, mole, 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 mole. And I get a nice little equation, 5 divided by 80 times 22.7. And I will get approximately 1.42 decimeters cubed of N2O. All right, so that is the answer there. Lastly, calculate the standard enthalpy change, delta H, of this reaction using section 12 of the data booklet. You need section 12 because while we have delta H for ammonium nitrate and while we have delta H for dinitrogen monoxide, by the way, these are delta H of formation. We also need delta H of formation of H2O because that's in our reaction too, which when we look it up in the data booklet, we find out that it's negative 285.8 kilojoules per mole. So what we're going to do is we're going to find the delta H of reaction by using our equation. And the equation that we actually use is that the sum of the delta H of the products minus the sum of the delta H of the reactants. And so when we plug this in, our products is going to be ammonium nitrate, or sorry, dinitrogen monoxide, 82 kilojoules per mole. And we're going to assume that we have 1 mole because we want to get rid of these moles times 1 mole. And we're going to add that to that of water, which is going to be negative 285.8 kilojoules per mole. Whoops, that's not per mole, per mole. But if we look at our balanced chemical equation, we have 2 moles of water for every 1 mole of dinitrogen monoxide. So we're going to say times 2 mole. All right, and that is our product. We're going to subtract that of our reactants, which is negative 366 kilojoules per mole. And we only have 1 mole. Again, I'm just using the balanced chemical equation. When I add this whole thing up, I get negative 124 kilojoules. And that is my answer. All right, that is the whole test. Hopefully this helps and have a great